Last lecture, what we had done was, well, we defined the cross-section in terms of this invariant matrix element M squared, and we looked at a simple case where we have two particles scattering into, well, in fact, anything scattering into two particles in the final state, and to just see how we can integrate over this Lorentz invariant phase space factor. And well, at the end, we kind of obtained a relatively simple expression. If you want to calculate the cross-section for scattering, a differential cross-section for scattering of the second particle, let's say, in a given direction, you just need to calculate this matrix element squared, multiply by the momentum, divide by factors that are constants or fixed by your initial state. If you fix your center of mass energy, if you are doing collision experiments and accelerators, P1, P2, they are all fixed. So if you measure the cross-section, you can basically obtain this invariant matrix squared, which, for example, in the first-Born approximation is nothing but the Fourier transform of the potential. So you basically, by measuring this M, you can determine the potential that the particles are interacting with. Okay, let me pass these. Then we started looking at what we mean by the scattering amplitude, and in particular we obtained this so-called the LSZ reduction formula. And let me just write down look at the final expression we have. Sorry, there's a correction here. These are omegas. Now, omega is the fully interacting ground state. 0 is the empty state, and they don't need to be the same. The ground state might have particles in it. Well, essentially what this tells me is that, just look at this n plus m point function. Again, they have to be omegas. So just look at this n point m function of the fields. We have these phi 1, phi 2, etc. They can be the same field, they can be different fields. You calculate that matrix element of that time-ordered product as a function of their position. If you are able to do that, just apply this Klein-Gordon operator there. What it will do is, in fact, those Klein-Gordon operators, you can just integrate them by parts. If you integrate by parts, what you will get is, with a minus sign, just p squared minus m squared. So if this matrix element has a pole at p squared is equal to m squared, its Fourier transform has a pole at p squared is equal to m squared, then when you multiply it with p squared minus m squared and then set p squared is equal to m squared, you will get a finite answer. And in fact, that will be what we are interested in. We have these ingoing and outgoing particles. They are on shell, so for them, their momentum squared has to be is equal to their mass squared. So there has to be some poles in this n plus m particle and n plus m point function at the locations of these particles. We are just picking by multiplying it with p squared minus m squared and then setting p squared is equal to m squared. We are picking up the residue at that pole, which is our S matrix element. That's basically what the LSZ reduction formula tells us. So basically what we are trying to do here is, okay, we have already, in a sense, our framework, the quantum mechanics framework. We had defined our states, the particle creation and annihilation amplitudes. We looked at what is called the old-fashioned perturbation theory. We know how to do computations, but you have already seen in class that it's a long computation. Or those who attended the problem-solving hours last week, it's a long computation. Doing it the old-fashioned way, and keep in mind that you are just calculating the first correction. There will be all other corrections that you will need to calculate. So what we are now trying to do is somehow get a more intuitive, more easier way to calculate basically the same thing. That is what we are looking for. And LSZ reduction formula is kind of our first step in that simplification of the computation. Now then we looked at we looked at the two-point function in non-interacting theory as an example. You see, here we have the LSZ reduction formula in general for an endpoint function. Whatever n is, you just have the product of n functions. So here we have just two functions, and this is a non-interacting theory. That is why I have all those zeros. And then when we calculated this two-point function, okay, this is what we obtain. Minus I times that exponent divided by k squared minus m squared. Well, my claim here that there have to be poles in our particles is kind of apparent over here. So there is a propagator, for the free case at least, there is a propagator. If I take its Fourier transform, it has the Fourier transform is 1 over k squared minus m squared. If I multiply it with k squared minus m squared and then set k squared is equal to m squared, I just get a finite answer. Well, this is a simple case where I just have a single particle coming in, single particle going out. So it's nothing so interesting, so fancy, but at least the pole, you can actually see it over there. And this also kind of shows us that we can do computation in the free theory. I don't really know how to do the computation in the full theory, but we can do some computation in the free case. And in fact, kind of that is what I would like to do first. I would like to, is there a way to relate this endpoint function of the fully interacting theory, this matrix element of the ground state of the fully interacting theory, to the endpoint function of, to some kind of a function of, let's say, not necessarily an endpoint function, to some matrix element of the non-interacting theory. That is what I will be looking for now, the first thing that I will do. Now then, because that will tell me that, okay, I have the LSZ reduction formula that tells me that if I'm interested in looking at the scatterings, I should be calculating these matrix elements somehow. And in the full theory. If I can relate it to the non-interacting theory somehow again, well, I know how to do the computation in the non-interacting theory. Non-interacting theory is simpler to solve. And then, of course, we will see how we can proceed with the computation. So any questions up to here? Any questions about the things that we had done before? So let me pick up this matrix element first. This is what I have. I don't know what these x1, x2, xn's are. They're just some labels or, about the positions of these operators. And remember, this is now in the Heisenberg picture. And x1, x2, xn are just names we gave to them. Well, I can choose my naming such that x10 is larger than x20, larger or equal to xn0. I'm not losing any generality because I'm just naming them. And within a time-ordered product, I can just change the order of my fields because essentially it's the time ordering that orders them, not in the order that I put them within the time ordering. Now, why do I do that? Because if this is the case, then this is my matrix element. Time ordering has already done its job. So there's no time ordering operator in this expression. Now, what I would like to do is, remember we had discussed about the interaction picture. Let me write in the Schrödinger picture. I have the operators independent of time. And then I have the states which depend on time through e to the power minus I h t minus t0 psi at t is equal to t0. This is how I define the Schrodinger picture. Then we had the Heisenberg picture. Where the operators depend on time through this equation. And the states are basically independent of time. This is the Heisenberg picture. This is the Schrodinger picture operator, Schrodinger picture operator, Heisenberg picture operator. And then we had something in between, so-called interaction picture. Well, in the interaction picture, I have the operators depend on time, and they evolve only under the influence of H0. And the states in the interaction picture, they also evolve in time. You see, the Schrodinger evolution would be minus I h t minus t0, psi of t is equal to t0. But this, I'm just separating out the evolution due to h0 in this time evolution. So I will multiply it with e to the power I, this operator. So this is what what we call the interaction picture operator. Interaction picture state.
And on the topic, we are, how can I say, using different pictures. Isn't, I mean, one of them is better than others? For example, interaction picture.
Depends on what you are trying to show.
Huh.
You see, for example, when I look at this matrix element, there are basically, well, this is in the full interaction. This is the phi's are the full Heisenberg operators, and omega is the full ground state of my system. Now, what does the interactions do? The V does. It changes phi's, and it changes omega. Because if there are no interactions, if the potential is 0, then I know that omega is basically the empty state. And phi's, if there were no interactions, the phi's, I know their evolution. So there are two things I don't know. I don't know how phi changes with time. I don't know how omega changes in time. So it will be better if we have, here there are two things and two unknown things. It would be easier, probably easier, let's say, if we would just have one unknown. So essentially, I would like to express this in terms of operators that I know, how they change. But interaction picture gives me that. So at least, since in the interaction picture, the operators are evolving under the influence of H0, I know how they evolve. That is known. So I will express this matrix element in terms of operators that I know, plus hopefully some corrections, which in principle I can calculate.
So for example, if you use a Schrodinger picture, that will be, that solve the, we will reach the same solution, but in harder way.
Yeah, if at all possible. So for example, here in this matrix element, we are already in the Heisenberg picture. Because I have all these operators at different times. Well, the Schrodinger picture computation would basically be this one. Remember, we are trying to calculate this one, which is given as f where the initial state we just wrote as square root of 2 omega ki, a dagger ki. We just wrote it in this form. A's are just our annihilation and creation operators, creating states in the vacuum, in the empty state, let's say. I have to solve this one if you want to stick with the Schrödinger picture. Now, if you can, well, be my guess. Now, that's a nice question because in general, actually, we don't really know what to do. We just try everything. And that is what we call research. You try to approach this problem in the Schrödinger picture, somebody else tries to approach this problem in the Heisenberg picture, another person tries to approach it in the interaction picture. Schrödinger approached this problem using what's called the old-fashioned perturbation theory. Feynman approached it within the interaction picture. And then it turned out that what we obtain in the interaction picture is much easier to remember, much easier to compute. And then some people claim that, I don't know if you have heard Unruh. He's a Canadian physicist, famous for the Unruh effect. And in a meeting, he was saying that one of the people that had done the worst damage to particle physics is Feynman. His claim is that, okay, Feynman diagrams and those computations are very easy to get the results, very easy to publish, so everybody is doing that. Nobody is now trying to find a different method. Okay, let's continue.
Unruh is a physicist or
Physicist. No, physicist. Basically, what he proved that if you are in an accelerated frame, vacuum is just a heat path. If you are in an accelerated frame, the vacuum is a heat path. So it's a non-trivial environment with finite temperature. Okay, let's come back. So what I would like to do is now convert everything into interaction picture. So this is my Heisenberg picture operators. Well, in this matrix elements, I have my Heisenberg picture operators, which I had defined as e to the power I h t minus t0, e to the power minus I h t minus t0. I would like to write this in terms of my interaction picture operators. Well, my interaction picture operators, if you look at this definition, the operator is sandwiched between e to the power I h0, t minus t0, e to the power minus I h0, t minus t0. Well, I cannot just insert whatever I want. I can at most insert identity. Now, if you look at this operator, well, that operator is essentially this operator over here, which is the evolution operator for the states in the interaction picture. And so this is, let me just call it U TT0. This is my interaction picture operator at the time t, and this is my U TT0 dagger. And keep in mind that, let's say that U TT0 times U TT0 dagger is actually 1. Let's say U T1 T2, U T2 T3 will be actually U T1 T3. Now let's go back to my matrix element over here. This is equal to omega u t1 t0 dagger phi 1 in the interaction picture. Well, I will omit the arguments x1, x2, x3 because phi 1 has argued the position x1, phi 2 has position x2, etc. And u t1 t0 u t2 t0 dagger phi 2 in the interaction picture u t2 t0 u t n t0 in the interaction picture phi n u this is dagger t n t0. This is what I have. Well, u t1 t0 u t2 t0 dagger is just u t1 t2. So what I obtain is omega u t1 t0 dagger phi 1 in the interaction picture u t1 t2 phi 2 in the interaction picture u t2 t3 u tn minus 1 tn phi n in the interaction picture u tn t0. It is nice because at least in the intermediate states between those field operators, there's no t0 left. Whatever you chose as t0, nothing really matters.
So, intermediate relation, correct? Dagger.
This one.
Yes.
It is. Well, how to see that? What is u t1 t0? We solved it. That is the time-ordered product, time-ordered exponential of minus I from t0 to t1 dt v in the interaction picture t. Well, let me write it slightly differently. I can write that integral as a sum. Sum over n, let's say epsilon vi n times epsilon. Which is product over epsilon, let me put pt, minus I epsilon vi n times epsilon. Well, let's say this is, let me just invent the term time-ordered product. What this is actually exponent minus I epsilon vi at the time t0, exponent minus I epsilon vi at the time t0 plus epsilon, exponent minus I epsilon vi t1. You see, within a time-ordered product, I can ignore the ordering. Time ordering takes care of the ordering. But if I can ignore the ordering, if I can assume that my operators are commuting, e to the power a, e to the power b will be equal to e to the power a plus b. This is correct as long as I can ignore the ordering of a and b operators. And within a time ordering operator, I can ignore the ordering. Time ordering will take care of which order they will be. So I can just separate this exponent of the sum to the product of the exponents, because of course I have to do a time ordered product of the exponents. That is what I did in this step. Or you can consider it this way. Let's say that you are evolving under a potential which depends on time, because we are in the interaction picture, or the potential can actually depend explicitly on time also. And so the potential at different times do not commute. So you cannot just write the solution straight away. But what you can do is you can just evolve your state or operator, whatever you are evolving, in steps, in time steps of epsilon at a time. So if that time interval is very small, within that time interval your potential is time independent. If it is time independent, well, you can just use all these tricks that you know for ordinary functions. So this just evolves your state by epsilon. Then you just evolve it by another epsilon. Then you evolve it by another epsilon. So if these steps are small enough, that will give you the full evolution. Of course, you have to take, I don't know, T1 minus T0 over epsilon steps. Now, what does taking the dagger does? It reverses the order. So what I will have is exponent minus I epsilon Vi of T1, exponent minus I epsilon Vi of T0, again, just steps of epsilon at each of the product. Now, I have as the same expression for this U dagger with I replaced with minus I in reverse order. So that will give me exponent I epsilon Vi of T0, exponent I epsilon Vi of T2. Well, these will cancel. And what I will end up with is exponent minus I epsilon Vi of T1, incremental steps exponent I epsilon Vi of T2, which is nothing but time-ordered exponent of minus I integral over time from T2 to T1, Vi of T, which is just U of T1, T2.
What if we change the position of U2 dagger and U2 U2 dagger operator? We cannot complete this kind of solution.
What do you mean by U, T2, T0, dagger?
Dagger, yeah.
Well, I'm happy that I didn't have that here.
Yeah, I mean, you don't have that.
Well, what you would get there, basically, these will come first. Or let me write this in this form. This is equal to U of T1. No. Okay, this will come first, fine.
Yes.
Then you will have this one. Well, there are no simplifications.
We do this just because we doesn't depend on time. I mean, potentials commit with each other so that we can.
No, I'm not assuming the potentials commit with each other. In fact, I'm assuming that potentials do not commit with each other. Potentials at different time do not commit with each other. That's the kind of the trouble I'm having, and so I'm just doing all these tricks. You see, if potentials were just commuting with each other, I don't need to have this T over there, for example. I don't need to worry about time ordering. Everything would be just ordinary exponentials, and I would be able to just simplify this also. But since I don't have commuting potentials at different times, I have to be careful.
This epsilon trick resolve all of my problems.
Well, that is what I'm using by integrals or just evolving by epsilon in time. I don't have any problem there. And it depends on what you mean by problems, because even there, VI's at different times do not commute. So I cannot just combine those exponents. If VI's did commute, I could combine those exponents into a one exponent. So let's go back. This is what I had. I'm still left with what is omega. Well, I'm not so happy with what I will do now. Let's say that, let's start with the empty state. Yes, at t is equal to minus infinity, at a very early time, let's say at t is equal to minus t, I have vacuum. The potential is zero. That's also the ground state. Now I turn on the potential very slowly. Well, that's an adiabatic change. And adiabatic theorem tells me that if you are changing your potential very slowly, if your system starts in the ground state, it will stay in the ground state of the new Hamiltonian, of the new system. It will always stay in the ground state, whatever that ground state is. So let me evolve this, again keeping in mind that I'm assuming I'm turning on the potential very slowly adiabatically. So if I evolve this from minus t up to t0, now at the time t0, let's say my system is interacting, I turn on the potential fully much before this t0, let's say. Well, that would just tell me that this is the new ground state. So I started with, at the far past, let's say, empty state, with my Hamiltonian, just the free Hamiltonian. I turn on the potential adiabatically, very slowly. And then I can use the adiabatic theorem that if you start in the ground state, it will stay in the ground state at all times, whatever your ground state is. That's what basically I'm using. And at the time t0, let's say we can even say that much earlier than t0, it is, my potential is fully turned, so my system is now in the ground state. I will also write one more thing here. This is identity. So I didn't change anything. So why did I write it like that? Let me put this over here. You see, this product is the evolution from the time minus t to the time plus t. Keep in mind that eventually I will take the limit that capital T goes to infinity. So now you see, I take the empty state at a very early time at min t equal to minus infinity practically. I turn on the interaction adiabatically. So if I turn it adiabatically, even at a very early time, my theory will be fully interacting. I've evolved my system, my ground state, in time. but remember it was in the ground state. It will evolve in time, it will remain in the ground state. Ground state is an energy eigenstate. So, but then at a very late time, I will start turning off the ground state, or off the potential again adiabatically. So my system will, even though my system is changing, my potential is changing, since I'm turning the potential to zero off adiabatically, my system will always remain in the ground state. So this evolution is still the ground state up to some phase. It will be in the ground state. That is all I know. I don't know if it will have the same phase or not. But I know that it will be the ground state if I turn on the potential and off the potential adiabatically.
What does this first one
Hmm?
do? When does it move? This adiabatic.
Come on,
slow and on and off?
you take 508.
I forgot. So.
Okay, there's a catch. You see, it has to be very slow. So what does very slow mean?
Quasi-statically.
What does that mean?
Slowly.
For example, one case where this will fail is when you have phase transitions. Because phase transitions, by definition, they are almost instantaneous. Nothing is slower than a phase transition. So if your system has some kind of a phase transition, it's not guaranteed that this will work.
This is the answer you gave in 508 as well, right? I'm asking, does anything change in by strength of interaction or something? Like, is this a good model for weak interactions blindly?
Well, you see,
Because-
it does work. Strangely, it does work. And if there are phase transitions, what you do is you basically do another trick, what's called the Kaldich formalism. So what he does is, okay, just give me a moment. Let me almost finish this.
Sorry, but when we do it, adiabatically, that means when I'm considering the first law of thermodynamics, du equals dv, right? dq because d equals 0.
No, here the adiabatic basically means that the changes you are making are slower than any characteristic scale of your system. That is what adiabatic means. So you see, within a very, the change in the potential, let's say, at any time, should be very much smaller than any possible energy change, for example. So why do I need this? Because I also need this one. That is what I want. This will be equal to 0 u t t 0 n. So this is the ket, this is the bra. Within this matrix element over here. Now, what is my matrix element then? My matrix element becomes the empty state. You see, this is not the ground state, or not necessarily the ground state of my system, but it's an empty state, no particles. Then I have u of tt0, phi 1, yeah, sorry.
N is with conjugate or not?
Where? I mean, I don't really care about that one, but to be formally correct, yes. Now, let me just make another comment. Instead of this t0, let me put it t prime. And keep in mind that t prime is arbitrary. I can choose a different t prime for this omega and a different t prime for this omega. The crucial thing, the adiabatic theorem tells me is this t prime should be at a time when the potential is fully turned on. That's the only thing I want. Because it will be, after that time, it will be in the ground state. If it's in the ground state, it will stay in the ground state of the full theory. Now, why will that be important? Because you see here, I would like that t prime to be t1. No, sorry, I don't even want that, sorry. It's t0. t1, t0 dagger. Phi of x1, u of t1, t2, u of tn minus 1 tn, phi of txn, u of t0, tn t0, u of t0 minus t, vacuum, then I have this constant.
There will be dagger, I guess.
Where?
T0 minus T. I know, okay.
Well, the first one is u of t t1, phi 1, u of t1 t2, u of tn minus 1 tn, phi n, u of tn minus t. So I start from minus t, evolve up to t, and the first time, the earliest time in my field operator, then act with phi at xn, then I evolve up to tn minus 1, act with phi of xn minus 1, etc., until I evolve in from time t2 to t1, act with phi 1 at x1, then evolve from t1 up to large T.
So we concluded that our ground state can evolve in time.
No, well, I mean, it acquires some phase, and all that phase is, let me put some tilde over here. Is in that factor, all possible phases. You see, ground state does evolve in time if its energy is non-zero, but the evolution will be just a phase. Again, keep in mind that what I'm trying to calculate here is the S matrix element. Because if I can calculate this thing, I can use the LSZ reduction to calculate the S matrix element itself. But
Is
now,
it not modulus square?
no.
Left and right, both right, cat, both of them.
Well, you see, I define the phase of my ground state so that this exactly is satisfied. There is no factors over there. But here I have the evolution of the ground state from minus infinity to infinity. There it will still be a ground state with an additional phase. I cannot redefine it, let's say.
And why you are not happy with what you are now?
I will come in a moment. Let me just finish this one first. Now, everything is time ordered here. But since everything is time ordered here, this is equal to 0. Time ordered product, phi 1, phi n. Remember, within a time ordering, I can just put operators wherever I want. The time ordering will take care of where they will actually go. But that means I'm just multiplying all these u's together, and that will just give me u from the evolution from minus t to plus t, which is nothing but the exponent minus I. Let me just take the t to infinity, dt vi of t. This is the matrix element I'm looking for.
So between the T1 and T2, the T2 to T3 is small again.
Not necessarily. You see, let me write it explicitly if you like. First of all, I'm just changing the order of my operators. I'm within the time ordering because what will determine the ordering of my operators will be not the place I put them, but the time ordering operator. So I end up having u of t, t1, u of t1, t2, u of t, n minus t. Well, this product, I don't assume that the T1 minus T2 is small or not. This product, whatever the T's are, is always going to give me T minus T, which is the time-ordered exponent minus I dt from minus T to T, the interaction picture potential. Now, again, the ordering doesn't matter within the outer time-ordered product, so I can just ignore that time-ordered in that exponent. So I will end up having my matrix element equal to now that will be some phase. Well, what is that phase? Well, I don't really care about that phase because I know one thing. I know that this should be 1. But that is just nothing. And this should be 1. So I know what that phase is. So, and which basically completes part of my proof, let's say. That is one step, this step. This is 0 time-ordered operators of phi 1, phi n times e to power minus I minus infinity to infinity dt vi of t time-ordered exponential of e. Why? Because the I of t, the potential, is nothing but the interaction part of my Lagrangian with a minus sign. My Lagrangian is the integral of the Lagrangian density. In fact, I can even write, let me just write this also as I achieve one more thing. You see, potential, if you talk about potentials or the kinetic energy, they are not Lorentz invariant.
Sorry?
Potential energy or the kinetic energy, they are not Lorentz invariant. But the Lagrangian is Lorentz invariant. That integral, that exponent, is Lorentz invariant. So basically, Lorentz invariant is now explicit in our result.
Sorry.
Well, our theory is Lorentz invariant, as we had shown in the old-fashioned perturbation theory. The final result was Lorentz invariant, although in the intermediate states, it didn't look like that. Well, the same thing over here. When we are writing it as V, it doesn't look Lorentz invariant, although the final result will be Lorentz invariant. But when you write it in terms of the Lagrangian, it is Lorentz invariant at all steps, or the Lagrangian density.
In all steps.
Yeah, in all steps, everything will be Lorentz invariant. And that is something we want. I mean, we want our theory to be Lorentz invariant. Well, the theory is Lorentz invariant, but we would like it to be Lorentz invariant at every step. Any questions before the break?
interaction part.
Okay, that's
That
V.
is- yeah.
Well, you see, what is not Lorentz invariant is, this is not Lorentz invariant.
Mm-hmm.
No, sorry. You see, this is not Lorentz invariant. I'm only integrating over the three space coordinates. This is definitely not Lorentz invariant. But now if I integrate it over time, you see, time integral itself is not Lorentz invariant. The potential itself is not Lorentz invariant. But the integral of the potential over time is something that is explicitly Lorentz invariant. This is explicitly Lorentz invariant.
We want this.
Yeah, no, you see, our theory is Lorentz invariant.
That's why can
We want it to be explicitly Lorentz invariant at every step. It will look nice. I mean, you can live without it. I mean, you can choose, we will be dealing with electrodynamics, for example. You can choose gauges which explicitly break Lorentz invariance. But gauge condition is not something physical. So although in every step of your computation you will have results which are which are not Lorentz invariant, which doesn't seem to respect the Lorentz symmetry, the final result will be Lorentz invariant. Yeah, it will be better if it is Lorentz invariant at every step. That is what we are looking for here.
Is there a hidden minus G? You know, square root minus G?
What do you mean by G?
No, Lorentz invariant minus.
Well, G, what you call G is -1 minus G is 1, square root of 1 is 1. So 1 is over there. We are working on flat space.
Yeah.
There's no hidden anything.
Just to clarify something, when we were doing old-fashioned perturbation theory, we added the entities for that potential. We added the retarded and the advanced case, and they both together gave us the Feynman propagator. But here, the time-ordered product handles that, right? The phi1 field become before phi2.
Everything will be here. Now, the only detail that doesn't make complete sense to me in this derivation, now this is basically the derivation in the book also, is this step. I have some doubts about that. Why? Well, basically because this is the initial state. The Schrödinger state at the time t0 is a special time that at t0 all states are, all pictures have the same state. But that means that first I need to evolve this by this operator, not the U. This is what my vacuum, my empty state becomes at the time t0.
Can't we label all pictures equal at minus t?
Hmm?
Can't we label all pictures give the same function, same ground state at minus t? Just shift our 0 to minus t, but we use this extra evolution.
Well, I mean, I did try a couple of things. None of them really convinces me 100%. 99% I'm convinced that this is correct. The result works. But I have slight, is it so, questions.
We take the conjugate to change the order of t and t minus big T, but we didn't put a minus to t prime.
Now, where did I change it? I didn't change the order anywhere.
We put the conjugate to change all this.
Where? Here you mean?
No, no, the 2 points. Oh,
Here.
yeah.
Why should I?
Since we apply conjugate operation, so we take conjugate operation to the outside, so the t
Mm.
time.
No, I didn't take anything. You see, this is identity. U times U dagger, the time evolution. That is identity. I just inserted identity.